let's take a look at another classic situation and what the basic Mohrs circle would look like associated with that. What we have over here is what's called a thin wall pressure vessel. And what I've drawn is one of these big propane or butane type tanks, right? It's cylindrical, long. On the ends, I've represented the ends as domes, cups, if you like that phrase a little bit better. And they're just sitting in this cradle right here. And so we're taking a look at what the state of stress is when this thing has been pressurized. And what you'll learn shortly, not in this lesson, but in a later lesson, is that that little state of stress is one where on one axis you're going to have a normal stress with no shear stresses, that's of sigma, and you'll learn what that model is, sigma equals something. And then in the other axis, you'll have twice the normal stress. So we want to go from here and look at what Mohrs circle would look like in that particular kind of situation, right? Again, as always, we're going to start with our two axes, our shear axis and our normal axis, okay? And so the shear axis, we always put counterclockwise down lower, and we'll put clockwise up on top. And then we'll have tension to the right and compression to the left. Now you might have noticed that I skewed this in a way that this axis is way over here to the left. But we get a hint of why that would make sense just because we look over here and everything on these 90-degree planes is in tension, right? And one of them is twice as big as the other, which tends to suggest Mohrs circle is going to get pushed over here to the right. And indeed, that will be the case. The way we're going to figure that out is we're going to find 2 points on orthogonal planes to each other at 90 degrees. And point A on this one will have a normal stress that's sigma, and a shear stress, well, there's none on that plane, so it's 0. B, on the other hand, would have a normal stress of 2 sigma and no or 0 shear stress. So I'll put a little slash through that 0 to differentiate between the sigma and the 0 value. And then we just go plot these over here, right? We've got point A at sigma, comma 0, and point B at 2 sigma, comma 0. There's your B, there's your A, right? And because they're 0 shear stress, those are the principal stresses. And we can find out that the average is right there at 3/2 sigma, right? Average between those two. That would be the origin of your circle, and your radius would be equal to sigma over 2, right? So boom, boom, sigma over 2 for the value of the maximum shear stresses. And then we just get our circle template out again, and we draw it in. Right? Not too bad freehand. Whoa, that's maybe not too bad, but it's not too good either. So I'm going to freehand wise do this again. Of course, you're not going to do any of these freehand. You're going to get your circle template out or a compass or something to do that. That's really, it's kind of icky. By my eye, that's horrible looking, but it'll serve the job for talking through this a little bit. Note again that as we go from the maximum tensile stress and go radially, rotate radially, we end up then at the maximum shear stress, which is 90 degrees in Mohrs circle. It's 45 degrees in real life. So if there were a shear problem to happen, I would expect that to happen on one of the 45-degree planes. If that's where the failure from if the material is a shear weak material, which in typical ductile metals is the case, then I would start to see some problems potentially in that particular direction. If it's a brittle fracture, then we're talking about a normal stress problem, and the maximum's here, so I would expect then a brittle fracture to happen on one of these horizontal planes, which is really the vertical normal from a big picture standpoint. And that's how we do these after action reviews of forensic analyses, and we look at the failed parts, and we can begin to start to figure out what might have been the cause of that particular failure.